Hi everyone, in this video I'm going to walk you through SemiAnalysis AI research from system to tokens, an introduction to ClusterMAX, InferenceX, and Tokenomics. For anybody who's interested in more details on any of these projects, you can visit our website at semianalysis.com, also clustermax.ai and inferencex.com for those individual projects. I'm going to walk through this presentation one at a time. We'll do a little bit of detail on ClusterMAX, how we got here, the current rankings, and walk through some of the technical side of some example tests that we run when we're testing neoclouds. Then we'll talk about InferenceX, basic introduction to how it works, understanding the Pareto frontier, meaning the performance results that we get from InferenceX, and then some additional features that people can use to make important technical decisions related to which GPU they're going to pick for a given workload. Finally, we're going to talk about tokenomics, where I walk through how we track the token provider consumer market, the supply-demand dynamics that exist there. And then we'll talk about some hands-on testing that we've done with some of the latest models. This presentation is current as of April in 2026. So first of all, ClusterMAX. ClusterMAX is a neocloud rating system, and as you may know, the word neocloud is everywhere right now. So where did we get this word and where does it come from? Well, SemiAnalysis coined that term neocloud in October of 2024 to describe brand new emerging cloud providers that were exclusively focused on AI customers and as a result on building some of the world's biggest GPU clusters. In that original article, SemiAnalysis walked through a lot of the details on how exactly these neoclouds are different than traditional hyperscalers like Amazon or Microsoft or Google, and what sort of technology they're using. In the first version of ClusterMAX, released in March of 2025, the article walked through a review of many of the top neoclouds in the industry through both hands-on testing and research in terms of interviewing customers to have them describe some of their experience, to really get insight as to why these growing businesses, companies like CoreWeave, Nebius, Together, Lambda, Crusoe, why they were getting so big and having so much success at the time. Recently, we released ClusterMAX 2.0 in November of 2025, which was an updated and expanded rating of that original ClusterMAX article, going from about 20 providers to over 80. You can see that on screen right now. Just by looking at the logos, clearly the chart has gotten bigger as we've gone through different versions of ClusterMAX, going from 1.0, 2.0 to the current version, which is 2.1, and having a total of 90 providers rated. It's important to actually dig into what makes a good neocloud to understand exactly what causes providers to rise up that rating tier towards the platinum tier, and what causes us to not recommend certain providers. And in this case, there's basically two ways to look at it. You can look at it from the lens of a customer's perspective, which is to say somebody is looking for a Slurm cluster, a Kubernetes cluster, standalone individual virtual machines, large bare metal clusters, or they really want to dig in on terms of like how people do monitoring of these clusters or how they implement health checks. In that case, we have on our website details related to our expectations for each of those 5 categories. And so you can just individually log in and see, hey, this is what we expect for a Slurm cluster. This is what we expect for a Kubernetes cluster. The alternative way to look at this is from the provider's perspective, which is to say, what are the critical dimensions that kind of can cut across any project and go beyond our hands-on testing, and really show how one provider is different from the other. And in this case, we identify 10 different dimensions: security, lifecycle, orchestration software, which is that Slurm or Kubernetes experience, storage performance, networking performance, reliability at scale, monitoring, pricing, partnerships, and availability. Clearly, 3 of those at the end are all just really about how the business operates on a day-to-day basis. And the first 7 can be a combination of discovery through hands-on testing, as well as conversations with users or customers of these cloud providers to understand their experience when it comes to getting support throughout the lifecycle of the system, or when it comes to assessing reliability over time, it's really important that you actually do things at scale instead of with our testing where we are testing at, in most cases, a maximum of 4 nodes in the cluster. So when I talk about testing, what is that testing that we do? For what it's worth, we are actively working on getting all of these tests to be open source, which means that we are going to have a GitHub repo where you can go and log in and see how to run these tests for yourself. And we're going to have a roadmap so that providers can really run audited testing for themselves without having to spend the time of actually like going in and doing this work hands-on. Today, with every single one of those 90 providers that we have rated, we've done some form of hands-on testing and definitely have working relations with the providers to get access to systems so that we can run this stuff for ourselves. So basically, there's 3 stages of testing that we do when we get access to one of those clusters. The first is this cluster audit, which you'll see on screen right now. And later I'll talk about performance testing and then reliability or burn-in testing. When it comes to an audit, we basically check to see that Slurm and Kubernetes are set up in a way that we would want to use the cluster. In addition, we review the monitoring dashboard to make sure that it's got all the information we would look for. On the Slurm side and the Kubernetes side, there can be things that are common. This is like having passwordless SSH to worker nodes and sudo access, or making sure that software is like installed and up to date, such as the NVIDIA Container Toolkit or NCU for performance testing, and really just like getting hardware counters on the system so that you can do performance optimization on low-level GPU kernels. But there are things that are specific to Slurm and specific to Kubernetes, and they're described lower down, specifically things like on the Slurm side, integration with Pixis or a topology configuration file, as well as a concept in Slurm called the health check program. And then on the Kubernetes side, it's more straightforward to get Kubernetes to be equivalent across different providers because Kubernetes is so common, and because it's updated so regularly, and there's so many like enterprise versions to build from. But in addition, when it comes to using Kubernetes, it's really easy to install or to customize a cluster, install software on a cluster or customize it to your liking. Whereas Slurm, you really need to work with the provider to get it to work for you. We really just expect Kubernetes to work out of the box and Slurm to work out of the box, regardless if we're using one cluster or another. Of course, there is a big dynamic in the industry right now to run Slurm on top of Kubernetes, in which case you'd have access to both options and ideally be able to schedule jobs on both the Slurm layer or the Kubernetes layer. Now on to performance testing. For performance testing, we always prefer to run real-world workloads. And so we run pre-training examples from Torch Titan. We use PrimeRL to mimic what real-world reinforcement learning looks like. And then we use our InferenceX examples, which are based on a custom benchmarking script, similar to a VLLM benchmark or an SGLang benchmark, to test throughput and interactivity across a range of different concurrencies. And so we run all of those on the cluster that we're provided in order to assess if we're going to get expected performance out of the box for the given GPU we're testing and the given network setup. Then we go through some micro benchmarks where we isolate individual components of the system. That's networking, storage, and on the next page, compute. For networking, we use nickel tests, the standard all reduce, all-to-all sort of tests, RICL tests for AMD clusters. And then we do read and write bandwidth tests on the individual links. And we also try to launch this through Python in addition to MPI, because both can be required on different clusters at different times and can behave differently depending on the setup of the network itself. In general, we have network performance that we expect. Typically, like for a simple H100 cluster, you're going to expect 8 400 gigabit NICs on every node, and you're going to expect to receive like the full bandwidth out of the box. Only providers that are really moving away from the standard networking or not setting up drivers correctly are really going to run into issues on these tests. On storage, we have some real-world benchmarks that we're working towards open sourcing. These are related to common patterns that hit storage in AI development. That's torch.save or distributed checkpointing.save, as well as a synthetic data generation test using video files, and then a simple test that we like for just like ergonomics of the cluster, where we time how long it takes to run import torch on the home directory. Interestingly, some file systems really struggle with this because they have a lots of small files issue. And then we also run the classic FIO, flexible IO, for sequential and random read and write IOPS testing, just to see what the maximum performance is out of the shared storage on the cluster. For compute, we test memory bandwidth. This is host to device, device to host, and peer-to-peer amongst the GPUs. We use Stas-Beckmann's MAMP finder, that's maximum achievable matmul flops on the GPU, kind of testing that we're seeing what we expect on a given GPU against the known best performance. This is based on top of QBLAS using Torch, so it's pretty well understood what's the maximum achievable gem shape, maximum achievable flops for a given optimal gem shape on a given GPU. And then we also have a custom gem benchmark that runs through group gems from some common model sizes or shapes, model architectures, and use Torch, Triton, as well as Deep Gem in order to implement this so that we can hit some different angles on the library that's actually running the gems. For lifecycle, we also have some additional testing, mostly related to the internet speed. We do a synthetic download upload test using speed test, but also pull from some common locations such as Hugging Face, Docker Hub, NGC, GitHub's container registry, and then we test pip using the pip install pulling from PyPy. We also try to add new users during the testing of the cluster. In many cases, providers have a nice CLI that you can use for this, or you can do it through the console, just upload SSH keys. In other cases, providers that aren't as advanced are forcing you to log in as a shared user, like the username Ubuntu, instead of authenticating you against the cluster using your IDP provider, like a Google Auth or Microsoft or GitHub or something like that. And finally, after all of this performance testing is done and we really have a good understanding of whether we would like to use the cluster or not, we run reliability testing. And in this case, we do an 8-hour burn-in that cycles through all of the previous tests so that you're testing and stressing a lot of the different components on the system simultaneously using those real-world workloads. In other words, you're having thermal expansion and contraction of the GPUs and the NICs at the same time. And then we log all of the thermals, the power, ECCs on the memory, link flaps, storage mounts, just to make sure that there's no issues during this burn-in test. And we end by injecting an XID error into a single system through a script that we've developed, and testing whether the monitoring systems from the provider actually pick it up and drain the node and swap it with a new one from a hot spare pool, or if it just sits there undetected. And we also reboot a node, or reboot all nodes in the cluster sequentially. And in this case, a lot of providers really can struggle to bring the node back into the cluster in the event that something doesn't work properly on their provisioning side. So finally, after all of that testing is done, in a lot of cases, we actually learn something quite important about the provider, which is to say, like, what the total cost of ownership should be. Providers that are higher on the rating system generally are able to charge a premium with respect to some of the providers that are lower rated. And so in order to accurately assess like how much that premium should be, we really need to understand reliability at scale. And so in our latest article, also kind of called ClusterMAX 2.1 from just a few weeks ago, we introduced a TCO calculator. You can see this on the website where you can input different pricing that you may have gotten from different providers if you're trying to make a cluster purchase today, and then integrate in measurements for good put expense. Good put meaning the impact of downtime, where lower tier providers have more reliability issues, experience more downtime, and therefore users are able to do less work on the cluster over time. For more info on those details, read the latest article or check out the website at clustermax.ai/TCO. Okay, now moving into the second section of this presentation, we'll talk about InferenceX. InferenceX is an open source automated benchmark that moves at the same speed as the AI software ecosystem. If ClusterMAX is recommending to people how to rent GPUs, InferenceX is helping people decide which GPUs to rent. Specifically, we test over 7 different models now, including DeepSeek V4 as of last week with the big announcement. And we test this across a number of different runtimes and hardware configurations. You can sort of see that on screen, how many different hardware configurations there are currently running DeepSeek R1, which was probably the most popular model being tested. In this case, we have runs across a suite of hardware. So from NVIDIA, H100, H200, B200, B300, GB200 NVL72, and GB300 NVL72. And on NVIDIA, that's across different software frameworks, VLLM, SGLang, as well as TensorRT, TRT with Dynamo. On the AMD side, we have testing done for MI300X, MI325X, and MI355X using VLLM, SGLang, as well as AMD's proprietary framework, Atom. In all of these cases, all of the data as well as the code to run these benchmarks is open source, which means you can check it out. The results on a daily basis, they're updated at InferenceX.com. And you can also see the code itself, the runs as people send PRs to the open source repo at on GitHub. InferenceX has been making waves in the industry. It is featured on stage at GTC 2026 by Inference King himself, Jensen Huang. You can see that one of the things we realized with InferenceX is actually how much performance improvements there are from generation to generation on the NVIDIA GPUs. And of course, NVIDIA liked that validation from us and used some of our data in their marketing materials. This is obviously, exciting to get the recognition across the industry, but it's also important, I think, because when you look at the results, this is putting data behind what sort of decision-making people have been making in the past, which is to say, for specific workloads, namely inference with large models at very high interactivity, meaning very fast output speed per user, the improvement in performance for the previous generation Hopper system to the current generation Blackwell systems is absolutely massive. And you can measure this on a per GPU basis on performance perspective, or you can measure it using the total cost of ownership, meaning how much the tokens would cost you to serve. As I said before, you can review all of these runs in our GitHub. And the reason this is important is because the software frameworks that actually run the latest models are evolving every single day, delivering continuous performance improvements on the exact same hardware. So the day zero support or the day zero performance that you're going to get out of the hardware on the new model is the worst it's ever going to be. In general, it's always going to improve over time, and those improvements can be very significant. Basically, if we dig into what we mean by this, it's also important to understand that there is a trade-off when it comes to serving tokens to customers. And that trade-off is between the speed at which you want to serve tokens to individual customers versus how many total customers you can support on a given copy of the model behind the API endpoint. And so this kind of introduces the concept of a Pareto frontier, which is to say that there is a curve that you can trade off between and measure different points on that trades between total throughput improving or throughput per user, using a term called interactivity to say how fast it is per user. This matters because inference endpoint providers who are operating models below the frontier are generally wasting resources and losing revenue. If they tune too much for throughput, they may be able to support more total users at a given time, but the outputs are going to be so slow that they're not going to be able to handle enough total requests. And in addition, if you tune too much to interactivity, performance per user, you may not be able to serve enough users total to be able to actually keep the systems busy, again, on a total tokens produced perspective. The other thing that's brand new as we introduce like the NVL72 systems and in the future introduce the SRAM machines like Grok and Cerebrus to some of these testing is that very high interactivity tokens can actually sell for a premium, which needs to be considered when you're trying to determine what is the optimal space on this curve or what multiple points across this curve you might want to serve. For example, if you're Anthropic, you might want to serve Claude tokens for Opus at the standard speed at a certain point and at the fast speed at a different point and at a different price point so that you can maximize the total revenue or the total profit that you're making on your inference endpoint business. There are many different charts on the InferenceX website, but two of the important ones to focus on here are in terms of total throughput trading off versus interactivity, and then TCO per million tokens versus interactivity. So on this first page, I'll look at the chart for total throughput, where basically on the left side of the top of the curve, you can see it's like a school bus. You're going to serve a whole bunch of different users, whereas at the bottom of the curve on the far right side, you're going to have very high interactivity, and you're going to be like a race car driving individual people very fast. Vice versa, when you look at the cost per million tokens, the school bus is at the bottom left of the curve because obviously individual tokens for individual users are going to cost very little for you to serve in terms of hardware time. And then for individual users, as you move to the right and interactivity increases, the cost per million tokens is going to go up. Now I'd like to walk through some additional features that are important for those InferenceX charts. When people are using this data, they use it for more than just determining which configuration to use for which hardware, for which model. They actually also just want to see this stuff over time. And so two things that change over time as new software gets released and improves performance is accuracy and performance itself. And so both of those things are tracked on the dashboard in different tabs that you can walk through and see for yourself. In terms of accuracy, if you look at the chart on the left, you can see that individual runs for a benchmark like grade school math, GSM 8K, can have different results for a given model over time, which means that some of the low-level kernel optimizations that you use on the runtime can actually cause numerical stability issues or other issues that degrade the model's performance. And so we want to be able to check that these evals are still performing as expected against the model endpoint. In this case, the initial one that we've done, GSM 8K, has a score of 0.95 or 95% for the DeepSeek V4 Pro model. And we just run exactly that benchmark at the different precisions, FP4 or FP8, depending on which hardware we're using, and all the runtimes to confirm that there's no issues and everything is scoring as expected. Watch out for all of this to improve over time as we run more of those evals in more repeatable ways. On the historical trends side, it's most clear to see this when we think about DeepSeek V4, which was only released a few days ago. And so I've got a screenshot of the chart on screen there that shows performance improvements of almost 3x in some cases in just 2 days. This is like a stark contrast and a clear explanation for why, if you hold interactivity isolated, if you isolate a specific interactivity, like you say, tokens per second per user is held at 30, people generally just want more throughput over time. And that's what software improvements deliver. In this case, the big chart or the big line going straight up and through that is GB200 NVL72, because clearly the very first day zero support for DeepSeek V4 was not perfectly optimized yet. And somebody unlocked something in a matter of days that improved that performance by 3 times. So looking for more of those historical trends over time is a real clear way to demonstrate how the software improvements can actually improve model performance, but as a downstream effect of that, improve the margins of many of these businesses. A couple more additional features as we bridge into the next section of this presentation that go beyond performance is that TCO calculator that I was just kind of alluding to, which is to say, what is the total cost of ownership of serving a given model endpoint per token? And in other ways to look at it is exactly which hardware is best for a given model. And so in this case, we provide a little bit of data on our assessment of how much hyperscalers, neoclouds, and others are spending for a given configuration. To do this, we lean on a historical snapshot from our TCO model, an institutional research product that we sell to many companies in the industry. And we also allow people to input their own values for how much cost is going to be for a given hardware platform. And so from that hardware platform cost, if you marry that with the actual performance level, you can get the result, which is to say, sometimes the very latest and greatest hardware is not yet performing at a level that would put its TCO at the most attractive level. And so you can view this in terms of like total throughput per GPU, the tokens per second per megawatt, or just the raw cost that you'd like to understand when comparing individual GPUs. Performance per dollar, in other words. And then the last thing to walk through is just that we're constantly adding new features. And so one of these things that is really cool is interactive diagrams. You can see that there's two on screen here, one for understanding the architecture of like the system, the GPU system itself, where you can look at the scale up or scale out topology diagrams on screen, in case you wanted to understand a little bit about what is driving performance out of a given chip and why a given model might perform better on one system architecture versus the other. And then another pop out there is architecture diagram for individual models themselves. So in this case, DeepSeek R1 is shown on screen, where you can see the different layers of the architecture of the model as you kind of walk through and kind of compare one model to another to get some understanding of where different attention mechanisms or different, layer counts or context sizes might be affecting performance when we compare models. Okay, all that talk about TCO. Now let's talk about tokenomics, where all this comes together. So in tokenomics, we track a number of different things. As I said at the beginning of this presentation, it's about the supply-demand dynamics in the token industry that has just been created recently. One of the kind of takeoff points that we've noticed recently, of course, is Claude Code. We wrote a newsletter article called Claude Code is the Inflection Point. So I've included a screenshot in this section of the presentation so you can see some of this research involves not super technical details, but just market level business tracking of what's going on in the industry. And it can be really compelling for people to make decisions in here. We call it a few different points along Claude Code's growth trajectory. This article is already out of date, being back in February. There's much more commits than this on GitHub. And just to be clear, this is only stuff that's public on GitHub and stuff where Claude Code is tagging itself in the commit body, or in other ways that we track it. But 4% of the public GitHub commits is an incredible amount to go to in just a matter of a few months. In addition to model usage increasing, we also see that the model release cadence is increasing. The screenshot's from a recent article where we show that if we track many of the top labs from both the US and China, you can see that February was a really big month, but April is already well underway in terms of how many models have actually been released that are coming to the forefront and very important. Some labs are busier than others, but in general, there's a lot of model releases happening right now. In addition, model performance is increasing. So we perform benchmarks and we also analyze public benchmark data. This is public benchmark data, and it's just a third-party dynamic chart that we provide to our Tokenomics subscribers so that they can see exactly who's winning what benchmark at a given time. And here you can see an analysis of GPT 5.5 actually taking some wins on some of the latest benchmarks, but other models like Opus 4.7 and Gemini 3.1 still hold strong on given benchmarks. In one of our articles recently, we included both these screenshots in addition to a lot of commentary on why benchmarks are bad, or at least giving an incomplete picture of what's going on in terms of these model releases right now. We're also tracking all of the labs quite closely. So we have data included in this model where we show that in the first quarter of 2026, Anthropic's quarterly ARR added actually overtook OpenAI's for the first time in a long time. And our model called a little bit of a evening out there, but we're going to continue to keep tracking these over time. We're also testing hands-on. So in one of our, again, latest articles called the Coding Assistant Breakdown, we went through some of these hands-on benchmarks that we did with our hands-on and sort of demonstrated a little bit of our approach, which can be different from what you actually see from the labs. And the example of some of these agentic coding benchmarks, we run these benchmarks without a harness to see the raw model performance, which can be interesting to compare to the model performance with a custom harness, which is exactly what the product is today, if you think about it in terms of using Codex or Claude Code. And in addition to that, we, of course, poll all of the engineers that work at SemiAnalysis to get their vibes, and many of the analysts, too. People who had not previously written code are now having interesting critiques of one model versus the other. And as you can see on the chart on the right side, we're spending a lot of money. Dylan tweeted this out, that we had a $30,000 day just a few weeks ago on the API endpoints. We're also analyzing a lot of this cost in the context of the tokenomics model. Our team in Singapore has built a number of agents that they use for research, and you can see some of the tasks that they've kind of identified in here and tried to assess exactly what the token cost was to perform the task that they did, as well as the human cost, the assessed human time that would have been taken, and the projected ROI. In this case, every one of these tasks that they do regularly, they assess as being over 10 times ROI, which is exactly the experience that we've had using these models, which is not that we are shrinking the company, it's that all the people that we have are doing a lot more with these models. And just to wrap up this presentation with a little bit of a summary, the result of all of this research, and really the motivation of SemiAnalysis itself, is to understand everything. And so on screen, you can see a stack that I'd like to walk through in a little bit of detail here now. This stack we call the AI Token Factory, and we build up the stack to try to get an assessment of the actual economics that we see. In this stack, we really are making some assumptions that you can change over time, but you build the layers of the cake up over time. And so the first layer is our BOM breakdown cost of a given layer of logic or HBM or the GPUs, the DRAM, the NAND, the networking, that all goes into actually building, in this case, a GB300 NVL72 system, and assessing how much it's going to cost per GPU hour in terms of the capital cost to buy that system and put it in a data center. Then on the next line, we go through the colocation cost, the electricity cost. These are common data points that we get from market surveys, and get the operational expense. So how much per hour you're actually spending to run those GPUs that you've purchased outright. You total those up to get a total cost of ownership for those GPUs. You assess the operating margin based on this level to get a rental price that we are tracking right now in the industry for long-term commitments. And then you start to build on top of that. So how much actual throughput are you going to get on a given GPU for a given model that we really care about? In this case, we use the DeepSeek R1 FP4 model because it's really the most optimized for this architecture right now, and the one that approaches the architecture of some of the biggest models in the world. Then we add on the rental cost, and we get a assumed utilization rate to really assess what the gross margin of the inference providers would be. And so in this case, we take a blended token selling price and compare it to the compute cost that it would cost to sell those tokens. And this token selling price is actually based on agentic coding traces that we've been tracking across the company, so that we can get a blended rate across input, output, cache write, and cache read pricing, which can be different on many different model providers. And anybody who's familiar with KV cache will understand this is really dependent on, as your requests get bigger, being able to read from that KV cache so that you're not spending all of that money on fresh input tokens or cache writes every single time. We then go down and kind of bring this on top to what individual users are paying for these tokens. And so not everybody is using the API at that price per million tokens there. But some people are using, products like all-in products such as Cloud Code or Codex that allow you to pay like one monthly price and then use unlimited tokens within some sort of rate limit. And so the assessment there is really the assessment of number of users that are running on the system, the average revenue per user, and then roughly the gross profit per user per month based on a application gross margin on top of these tokens to get a total, analysis that we believe is really complete. We believe there's really no place to get this level of research that has the amount of detail that we have, all the way tracing it through from, the design and the manufacturing of the systems to the build of the data centers and the operations of the data centers themselves, to the TCO, the total cost of ownership analysis of the economics of some of these neocloud providers, to the performance of the inference endpoints from first principles of understanding how these models run on these GPUs, to the final assessment of how these businesses are operating at scale. How profitable are they? How scalable are they? And how much room do they have to grow in the future? So hopefully you guys enjoyed that walkthrough of this stack and really this presentation as a whole as I bring it to a close. SemiAnalysis, we obviously sell our industry models and research, which is the foundation of what we do here. But our open source projects such as ClusterMAX, InferenceX, and our data, Tokenomics being one of those industry models, is really what we use to build all of this and bring it together. SemiAnalysis is very excited about everything that's coming in the token supply, token demand, ClusterMAX, NeoClouds, and InferenceX performance measurements on GPUs as we look forward to new hardware, new clouds launching, new models. And it's an exciting time to be looking into things. So thank you for your time listening to this presentation, and hope it was interesting, and look forward to any feedback. Thank you.